Hello everyone, welcome back to my channel. I would like to start a series of tutorials to understand LLMs in detail. As you all know, ChatGPT has taken the world by storm, showcasing its capability in generating high quality text. Moreover, ChatGPT is being used as a general problem solving tool where you can ask it, for example, to write a story or a poem or even a piece of code. In this series of tutorials, you will get a clear understanding of how these systems are trained, what type of data is used, etc. As a good starting point, let's go and understand the paper Learning to Summarize from Human Feedback. This paper was published back in 2020, and this paper is coming from OpenAI. So the title of the paper says two main things here. So basically, the title says Learning to Summarize, which means the idea in this paper is to build a model that summarizes a specific input, for example, and from human feedback, basically it tells you how do we use the human feedback of these summarizations to improve the system itself. We will see an interesting approach called RLHF, which is what is used to train systems like ChatGPT and GPT-4, etc. And we will understand this RLHF algorithm in detail. And the overview of the tutorial is as follows. First, we'll see the introduction of the paper, and we'll see the proposed approach. We'll see the experiments and results at the end. Now, as you all may know, the LLMs are basically pre-trained models which are trained to predict next word in a text. And these LLMs are transformer based, for example, and basically they take some input. Let's say I am going, and their job is to predict the next word. So if the LLM is good, it's going to predict something like to school, to office, to the beach, or something like that. But if it predicts something like a computer or a laptop, then the LLM is not good. So, and these LLMs are trained on huge amount of data. For example, ChatGPT, for example, is trained on a huge amount of text data, and similarly other type of LLMs. And once these LLMs are trained on such a large amount of data, they may not be able to do exactly what you are asking. For example, if you directly use these LLMs for summarization tasks, they may not be as good as, let's say, a fine-tuned or a supervisedly trained neural network model. So this problem is called alignment problem, where we are expecting the LLM to predict what humans prefer. And for that, sometimes we adopt for something like supervised fine tuning, where we take this LLM, which is pre-trained on just huge amount of unsupervised or unlabeled data set, and we then fine tune them to a specific task, for example. So this fine-tuned, supervisedly fine-tuned LLM, which is trained on a dataset D, which will have X and Y pair. So X is being the input and Y being the output. And for summarization, it could be as simple as X could be some text and Y could be the summary of that text. If you have this amount of this data set, you can simply fine tune this LLM to obtain a more tuned version of this LLM, which works best for your case. However, there is a new approach where we are going to use human preferences rather than using this old classical supervised fine tuning. We are going to use reinforcement learning approach where we train a reward model which will predict basically a reward score for a given summary and post, for example, and that reward is used to tune or to train the LLM. And that approach is called RLHF. We'll understand that in detail in the coming slides. But just so you know that we are not going to stop at this SFT, but we are going to align this LLM towards human preferences. So that's why we call this as alignment problem. And the data set is collected from human feedbacks, and those feedbacks are used in some form using this reinforcement learning technique to tune these LLMs towards those preferences, those human preferences. So the data collection is basically collecting a high quality data set of human comparison for different summaries or between summaries. And this system basically, after trained, outperforms the supervised fine tuning approach on TLDR dataset. So the TLDR dataset is basically the too long didn't read dataset from Reddit. And we'll see how the dataset looks like, the size of the data and so on in the later section. But on that data, this system performs or outperforms the previous approaches, which is, for example, the supervised fine tuning approach. The model also generalizes very well to different types of data set. So, for example, the model is trained on the TLDR dataset, but when it is evaluated on the CNN/DM news article dataset, it generalizes very well, and it also outperforms the previous supervised fine tuning models. So that means this approach basically is really good in generalization and also captures out of distribution or also generalizes to different distributions of the data sets. Okay, now let's understand the proposed approach in detail. We'll split this into four different sections. First, we'll understand the high-level overview of this paper. So basically the approach, and we will see then the data set and the task at hand, and then we'll see how the human feedback collection works, and finally we'll see the models. The models is basically an interesting, very interesting section. This is where we will understand this RLHF approach, which is what is used to train systems like ChatGPT. So if you want to understand how ChatGPT works, so please wait till the model sections. So okay, so the eye level overview looks like this. So basically, this is three-step process. So what we do is we take the data set. As I said, we take the Reddit TLDR dataset, which contains a post and a human written summary. And with that dataset, what we do is that we sample from different models and get a different summaries for every post. So imagine I have a post and there is a human generated summary, and also I can generate many different summaries from different models, they say different policies, which is basically different types of models, or from the same model at the initialization and after training, or from the middle of the training and so on. So with these various approaches or various policies, you can extract a lot of varieties of summaries for that specific post. Now the job of the annotator is to rank which one is better. So basically, if I send 10 summaries for one post, their job is to say which one is better. So they say, for example, let's say J is better than K. So imagine in the ideal, for example, in a situation where you have only two summaries, the job is to say which is better. So in that case, they say one is better than two or two is better than one, something like that. Now, once you have this type of data set collected from human judgments, so this is the human preference data set, right? So now what we are going to do is we are going to train something called a reward model. So the reward model is basically another LLM, which can be initialized from the SFT model. So we will go through or we will see in model section how these transitions happen, like from how we start with the pre-trained model and how we get to the final RLHF trained final policy. But but just assume that this model is also kind of an LLM initialized, or not really LLM, it's initialized with an LLM, SFT LLM, let's say. SFT is basically supervised fine-tuned LLM. And in the last layer, we just replace the token level prediction or the probability distribution layer by a linear layer which predicts a score, a single value. So basically, it's a single neuron, and it gives you a value or a scalar value, for example, right? And how we train this model is with this loss, where we, for example, since we have this data set where we have the human preferences, we feed the summary and the post to the model and get the score. And We do that for both the preferences. For example, if you have a J, since the human says J is better than K, we want to increase the reward for J and reduce the reward for K, because K is not good and J is good. So that's why I want to reduce the reward for K and increase the reward for J. So this is the typical loss function. And with this loss function, we will see the actual equation in the later section when we go to the reward model section. But the loss is computed like this. So once you train this model with this reward model, now we have a kind of a system which mimics human preferences, right? So basically what that means is, since we collected a data set for human preferences, which says which summary is better, in which summary is better. Now once we train the model, so basically we are mimicking that behavior. So that's why it is sometimes also called a preference model, or instead of reward, it's a preference model, human preference model. So what it does is it takes a summary and tells you whether it's better, or whether it's good or not in terms of binary value, but in terms of a score, a value, a reward value. So if the reward is higher, means it's good. Reward is lower, means it's not good. So that is the second part, or the second step. Now, once you have this reward model, what I have to do is I have to now update or improve the original LLM, or the original LLM. So how we do that is with this pipeline. So what we do is we use PPO, proximal policy algorithm, policy optimization algorithm, which is a reinforcement learning technique for updates. So this policy here, which is basically a neural net, is the policy we want to train, or policy we want to improve, update. So what we do is we take the post, pass it through the policy, then we get a summary. So this summary is sent to the reward model, and that reward model gives you a reward value. So this reward value is used to update our policy. We will see how the equations and how the optimization is done in later, but just so you know, so this is how the pipeline works. Feed the summary into a policy we want to train, and from the policy you sample the summarization, and the summarization goes to a reward model, and the reward model, based on the reward model, we want to update the the policy. And we will see how the equation and everything looks later. But once you do this process, once you train this system with this approach, you are going to get a much better LLM, which will generate high quality summaries. And those summaries will be better aligned with the human judgments. Okay, so this is the high level overview. Now let's go and understand what the dataset looks like. So the dataset is basically the TLDR summarization dataset that contains up to 3 million posts from reddit.com across variety of subreddit or topics. So these subreddits contain, let's say, a post and the TLDR post and the summary. So that's the dataset, and they also the paper basically filters some of the posts where the summary contain between 24 to 48 tokens, and also they whitelist subreddits that are understandable to general population and discard the ones which are complicated. So with that filtering, you will have the final data set, which is about 120,000 posts and summaries for those posts. And also they use the second data set called CNN/DM, which is a news summarization data set, and they use it only for evaluation and not for training. This is to measure the generalization of the approach. Then the so the task, I mean, as you know, it's to produce a model that is very good at summarization, and those summarization whom humans prefer. So and the paper says the quality of the summaries is judged by how faithfully the summary conveys the original post to the reader, who can only read the summary and not the full post. Okay, this is one simple example of the data point. So from the subreddit, you have the dating advice subreddit. You have one post where a person is asking about dating advice, and the human written summary in that post is basically this. This is also not sometimes really good. even though it's human generated. Sometimes when you actually ask a labeler which one they prefer, they might say an LLM based one is better than the human one. But we will see those results later. But just to see the example in the data set, this is how the human written summary looks like. And if you have SFT model, which is supervised fine-tuned LLM, it looks like this. And if you use the human feedback model, which is the pipeline I explained just now with the reward model and so on, you will get much better summary. And collecting human feedback is just what I explained. I think I'm going to skip this one. Now let's go to the models. This is the most interesting section. So models, there are mainly four models here. So we will understand each one of them in detail. So the pre-trained model is basically the LLM, the original LLM you train to for the next token prediction task. So if you remember what an LLM is, or just an LLM is, so language model, if you see the history of starting from Ngram language model till these GPT-4 or whatever. So the idea is very simple. So given n words, what is the probability of predicting n plus one word? Or what is the probability of the n plus one word and n plus two word and so on? So basically it's a prediction problem where the context is the previous words, or the context is the amount of words given at a particular time, and you have to predict the future sequence. A large LLM or LLM is basically a large language model which just uses huge number of parameters, many transformer layers, and that those models are called large language model. But the idea is very much same. So for the pre-training, what they do is they take huge amount of text data available in the internet, and they train this model to predict a next word or a sequence of next words given n number of words at the input. And when you train this system, you get a pre-trained LLM, pre-trained let's call it as pre-trained LLM, which is which sometimes works well even at the zero shot cases. For example, when I say zero shot, let's say you have this pre-trained LLM. What you can do is you can simply query, or you can simply create a sentence. Let's say write a summary for this specific post, and you can also, for example, add a context saying, okay, this is how the post, the other type of examples look like, and you can ask it to generate summaries. So people have shown that these type of large language models works well on in zero shot setting as well, but not as good as the supervised fine-tuned models. So we can use this pre-trained model to fine-tune or to get a SFT model, which is basically fine-tuned on some data set. So as you know, we have this TLDR data set. So this TLDR data set is fine-tuned, or is used to fine-tune this pre-trained LLM. And this, once you do the fine-tuning, so basically fine-tuning is basically, as you know, it's a same concept when you think about, for example, fine tuning a bird, right? So you have input, you have output, you just need to fine tune the model towards that. So with that, you will get SFT. That we also use it as a baseline. And the reward model. So reward model is basically the model trained on, let's say, the human preferences, where the humans compare the summaries. And the human feedback policy model is basically the final model where we use the reward signal and compute the reward score, and then use with that reward score we use the PPO to update the policy, the on policy model, which is the original SFT model. And we will explain these each one of them in the next section. But just a note that all of these models are GPT-3 style, which are basically the transformer decoder only models, and the human feedback experiments are also done on 1.3 billion and 6.7 billion parameters models. Okay, pre-trained models. As I said, the large language models are trained to predict next word, next token, and these models sometimes are used as zero-shot baselines for summarization task, where you don't need to train or you don't need to show any summarization data at all. with just asking a question about, okay, tell me the summaries for this, it will be able to generate something, and we can use that as a baseline. Uh, this is the pre-trained GPT-3 model, let's say GPT-3 or GPT-4, whichever, which is basically a large transformer model trained on huge amount of text data available on the internet. Now, supervised baseline. So the supervised baseline, sometimes they also call it as SFT, so supervised fine-tuned model, where we fine-tune these pre-trained models on some supervised data set. For example, the TLDR data set we have. So the TLDR data set, as you know, we have the summary, sorry, we have the post and the summary, and we just want to make sure the model basically tries to predict or learns from that data set so that it generates better summaries on the evaluation data set. And and once you have this, once you train this SFT model, you can use it for many different purposes. One is to sample initial summaries for collecting comparison. As I said at the beginning, when I was explaining the high-level overview, we sample the summaries from different policies to to grade from humans which sample is better or which summary is better. So you can use this SFT model also for that purpose. And then we use this to initialize our policy, basically the final model we want to train, and also the reward model. So the reward model, as I said, we use the SFT model. We just plug in the linear layer on top of the model that just predicts a single score, a single value. And we obviously use this model for the baseline evaluation. So we go from pre-trained GPT-3 model with, if we use the TLDR data set, we get this SFT GPT-3 model. Okay, reward model. Now, reward model, as you know, is trained on human preference data set. So I call it sometimes as preference model, but it is called reward model. So the reward model is basically same as the GPT model, but it is sorry. I think in this section I said something about replacing the last layer. We don't do any replacing of the last layer here. So basically, this model, this specific supervised fine-tuning model is obtained by fine-tuning the pre-trained model for this TLDR dataset. In the reward model, however, we take the fine-tuned SFT model, which was trained in the previous SFT approach, a supervised fine-tuning approach, and then we attach a single linear layer, which basically gives you a single score, a single reward score. So they call it reward here. So this score we get from this model for that specific summary is called R, right? So, and that's a single value. Now, how do we train this model? So we start from the SFT baseline where we initialize this reward model and then randomly add a linear head that outputs a scalar value, like I explained here. Then the model is trained to predict which summary among two summaries, for example, Y0 and Y1, is better as judged by the human. So if, for example, let's say Yi is better than Y1 minus I, so what we do is we compute the reward using this model for this pair, and then we compute the reward for this pair. Then we take the sigmoid of the difference. So if so basically the constraint is that we want to make this reward higher and make this reward lower. So in that case, we have the overall value which is higher. So that way the model basically learns to predict better rewards or higher rewards for a post or for a summary which is better judged by humans or better preferred by humans than the one which is not preferred by humans. And the expectation is over the data set, where the D is the data set, and for a ith sample, where you sample, let's say, X post X, and two summaries for the same post, y0 and y1, and where yi is basically the preferred summary over y1 minus I. So this is the loss, and then you train the model. And as you know, it's very simple because it's the loss function. And then you have the model, and you just train the model with, let's say, stochastic gradient descent, and then you have this reward model. Okay, so now that we have the reward model, what we want to do? So once we have this reward model, we want to use the rewards generated by the reward model in some way to update our preference, our policy. So the policy is basically our original SFT model. So let's understand this equation clearly. So basically, the pi SFT is our original SFT, the fine-tuned model, supervised fine-tuned model, which predicts a summary y for a given post x. And then we have on policy, which is basically the one we are trying to update, which is called phi here. Y, which is for the y, which is summary given the post, and it's also called RL here. This is the new model we want to create or we want to update. And we have some factor beta here. This is actually KL divergence, right? Kullback-Leibler divergence. And then here, r theta of x comma y, where theta is the reward model. Basically, this term gives you the reward score for the post x and the summary y. And the final reward we have for this post and the summary y is basically the sum of the reward and negative value with the beta of the KL divergence term. So what does it say? So the KL divergence tells you two things. One is don't push or don't update the model so that the parameters are too far. Parameters in the sense, let's say I have this SFT model. I don't want to diverge too much from this SFT model, because the SFT model, as you know, is trained on huge amount of unlabeled data set, and we all know it gives you it is good in generating some general text. But if you just going to change this SFT model or completely or update the weights into completely different distribution, then it's not a good thing. So that's why the basically we have this penalty term here, which is the KL term, which says don't push too much from or don't go too far from the original supervised fine tuning model. And it also helps us in avoiding mode collapsing, because if the model finds a region where it gets higher reward and it gets stuck there, it's going to be useless. And this is why this penalty term is useful. And then obviously we have this reward, which is basically predicted from the reward model, and we want to increase this. Now I took this image from one of the posts from Hugging Face. This is actually really nice to understand what's going on here. So here we have the initial language model, right? So the initial language model is your, for example, SFT, Pi SFT. And this is the model we want to update, which is called phi, Pi phi, right? And we have the reward model. As you know, we trained it in the previous slide. And this reward model gives you a reward value for, let's say, you have input X, the dog is, and the preference model or the policy will generate something and specify or something that goes into the reward model, and you get a reward. This is the reward. Now, with the initial model and the new model, we are going to compute the KL term. So the KL term, as you know, the pi PPO is what is called pi phi, and pi base is your original SFT model, and you have this KL term here, and we are adding it as a penalty term to the original loss function. So basically, this term minus this overall term is your final loss, and that loss we use that loss to update our model, our on policy model by phi using the reinforcement learning update, example the PPO, or you can also use reinforce. This is how the overall training of this human feedback policy system works. I hope you guys understood. Now let's jump into the experiments and results. So from the picture, you can clearly understand this picture or this results is there in the second page of the paper. I think it was not even in the result section, but in the second page. But this can clearly tell you already that if you use this human feedback approach, you are going to get way better results compared to even reference summaries which are written by humans. That is amazing, right? And it just performs much better than the supervised learning approach, which is this green line here, and the pre-training is obviously lower than the supervised fine-tuning, and the human feedback always works much better. And I also have this table here, the diagram about the validation accuracy of the reward model, basically. So the performance of the reward model. So as you know, like I told you at the beginning, what we are trying to do or what we are trying to model here is we are trying to model what humans prefer for these summaries. So basically, you are collecting a data set and training a model, but at the end of the day, we want to mimic this human's behavior. So humans, if for example, let's say prefer some summaries over others, and if we have created data set in such a way, we should be able to transfer that data set into a model and should be able to generalize them. So this diagram basically shows that if you have a big enough model and big enough data set, you can almost reach humans baseline. So with this 64,000 examples and whatever model size you are already approaching humans baseline, which is also not so great. It is just between 80 and 75, but ensemble of humans, because sometimes humans preference changes from person to person. So ensemble basically also is also not 100% accurate, because I mean, as you know, humans they have different preferences. It differs from personality to personality and so on. So but overall, as you can see, we can basically, with good enough model, we can actually predict human preference for a given summary once you train this on a big enough data set and big enough model. Now we'll see the another results for the CNN DM dataset, where we basically take the fine-tuned model, the human feedback policy model, and just use it to evaluate the CNN DM dataset. As you can see here, supervised transfer. So the human feedback, as you can see here, works much better than both pre-train and supervised transfer, but it is not better than the reference summaries. Um, that is another. So this also shows that even though you have not trained the system on this data set and you just evaluated it, the model actually generalizes very well. So in fact, the reward model actually generalizes very well. So the policy also has learned that behavior, which means the overall system or the overall pipeline works very well and generalizes very well. And that's all for this tutorial. Thank you so much for watching the tutorial. If you have any question, please drop in the comment section. I'll try to answer them. And hopefully in the next tutorial, I'm going to cover the Instruct GPT paper, which is somewhat similar to this paper, but with way too many tasks and way too much amount of data set. But we'll try to cover that in the next series. And thank you very much for watching this tutorial.